Jai Hind. I am Nidhi Singh, Assistant Professor in Electrical Department, Ajay Kumar Garg Engineering College. Today, we will discuss topic from Unit 2, that is 8086 architecture, and the subject code is KEE602, which is microprocessor and microcontroller. So first, coming to the features of 8086 microprocessor. So the 8086 is a 16-bit microprocessor. 8086 has 16-bit data bus, so it can read data from or write data to memory and port either 16-bit or 8-bit at a time. And 8086 has 20-bit address buses, so it can directly access 2 power 20, which is equivalent to 1 megabyte memory locations. So each memory location is a byte wide. Therefore, a 16-bit words are stored in 2 consecutive memory locations here. 8086 microprocessor can generate 16-bit IO address, hence it can access 2 power 16 IO ports. 8086, it provides 14 16-bit registers, and 8086 has multiplexed address and data bus, which reduces the number of pins needed, but it slow down the transfer of data, which is a drawback. So if we now coming to the architecture of microprocessor, it is internally divided into 2 separate functional units, and these 2 units are bus interface unit and execution unit. So in short, bus interface unit is BIU and execution unit is written as EU. These 2 functional units can work simultaneously to increase system speed and hence the throughput. What is now throughput? Throughput is a measure of number of instructions executed per unit time. So this is throughput. So it also increases the throughput. Now this is the architecture of 8086. So here you can see that this is a bus interface unit. This is a bus interface unit and this is a execution unit. As I told you, the whole architecture is divided into 2 parts, the bus interface unit and the execution unit. So we will discuss all the parts one by one. So bus interface unit, what is the function of bus interface unit? The bus interface unit, it is responsible for performing all external bus operation. So all the external bus operations are performed by the bus interface unit. And this bus interface unit, it sends out addresses, fetches instruction from memory, it reads data from ports and memory and writes data to ports and memory. See, so all these are the functions of bus interface unit. So in simple word, we can say that this bus interface unit handles all the transfer of data and addresses on the buses for the execution unit, right? So it is handling all the transfer of data and addresses for the execution unit, the other part of the architecture of 8086. So now coming to the execution unit. So now what is this execution unit is? The execution unit of 8086, it tells the bus interface unit where to fetch the instruction or data from and decodes instruction and execute instructions. So it tells the bus interface unit from from where the instruction is to be fetched. It decodes the instruction and it executes the instruction. So this is the function of execution unit. So execution unit contains control circuitry which directs internal operation. Here a decoder in this execution unit translates instructions fetched from memory into series of action which the execution unit carries out, and the execution unit has a 16-bit arithmetic logic unit, that is ALU, which can add, subtract and the logical operation. So the arithmetical logic unit means it can perform the arithmetic operation and the logical operation. So addition, subtraction, all these are the arithmetic operation, and or XOR, these are all the increment, decrement, these are all the logical operation. And so the main function of execution unit is to decode the instruction and to execute the instruction. So the different steps followed by execution unit is, the execution unit extract instruction from top of queue in bus interface unit. This we will discuss in coming slide. It decodes the instruction, generates operands if necessary, passes operands to bus interface unit and requests to perform read or write bus cycle to memory or IOs. It performs the operation specified by the instruction on operand. So now how this EU extract instruction from top of queue in BIU, here we will see while here the 8086 has actually the pipelining architecture. While the execution unit is decoding an instruction or executing an instruction which does not require use of buses, the bus interface unit fetches up to 6 instruction bytes ahead of time from the memory. So while the execution unit is decoding the instruction or executing the instruction, so while decoding and executing the instruction, the buses are not used in that. So buses are free. So when the buses are free, what bus interface unit do? It fetches the next instructions, right? So the bus interface unit stores these prefetched bytes in the first in first out register set called a queue. So when the execution unit is ready for its next instruction from the queue in the BIU, this is much faster than sending out an address to the system memory and waiting for memory to send back the next instruction byte or bytes. But there is an exception if we are using jump or call instruction. So here the we have to clear out the queue, because we know that in for jump and call instruction we have to go to some other location, right? So except in case of jump and call instruction, where the queue must be dumped and then reloaded starting from new address. So this prefetched queue scheme greatly speeds up processing, or otherwise it is very useful. So fetching the next instruction while the current instruction execute is called pipelining. So this is an important term. What is pipelining? It is fetching the next instruction while the current instruction is, we are executing the current instruction. So here we can see, like in 8085, what we do? We fetch instruction, we then decode instruction, and then we execute. So when the execution finishes, then again we fetch next instruction, then decode it and then execute it. But in case of 8086, what we do? We fetch the instruction, we are decoding, we are executing. While we are decoding and executing, we are fetching the other instruction. Similarly here, then we are decoding and executing the next instruction, then we are fetching the third instruction, right? So here you can see that we are saving this much time here, while if we are using pipelining. So in 8086 we are using the pipelining architecture. So here we can see like here the bus interface unit first fetches the 6 instruction in this instruction stream by queue. So this is a first in first out. So this is the first instruction which is in this queue. So this instruction will first come out. So it will fetch all the instruction, this queue will be filled, and the execution unit will take this instruction and will decode and execute it one by one. Now coming to the register organization. So the 8086 registers are classified in general data register, segment register, pointers and index register, and flag registers. So it is classified in 4 types of registers. So here general data registers, this is the structure, then segment registers, this is flag, pointer and index register. We will discuss all these registers one by one. Now coming to the register organization. So in architecture, here we can see where all these registers are located. So here we can see that these are the 8 general purpose register, and they are labeled as A, H, A, L. H stands for the higher byte and L stands for the lower byte. So if we talk about AL alone, it is of 8 bytes, right? This is 8 byte, and again this is 8 byte, and if we combine this AH and AL, then this is a 16 byte register. This is a 16 bit register. 8 bit, this is 8 bit, and this is a 16 bit register. So again, this BH, BL, all these are the 8 general purpose register. So we can use as a 8 bit, or we can use as a 16 bit. Now this part, these are the four segment registers. So this ES, CS, SS, DS, code segment, stack segment, extra segment, and data segment. This is CS, this is SS, this is ES, and this is DS. And they are used to hold the upper 16 bits of starting address that 8086 is working with. So they hold the starting address of the segment. Actually, the memory we have divided in different segments, so it contains the starting address of that segment. Now coming to the next part, this is the instruction pointer. This is related to the code segment. Then this is a stack pointer. This is related to the stack segment. And then these 3 registers, they are base pointer, source index, and destination index. Then here we can see we have a flag register. So now we will discuss all this register one by one. So flag register, coming to the flag register, here you can see that this is a 16 bit flag register. In 8085 we have seen that in 8085 we have a 8 bit flag register. So here this is a overflow flag, this is a direct flag, this is interrupt enable, this is trap flag, and this is a sign flag, then zero flag, then we have this one is auxiliary carry, then we have this is a parity flag, and then we have a carry flag. So all others are unused. This cross marks means these are the unused bits. So here we have total 6 status flag and 3 control flag. So this carry flag we have already seen in 8085. So this carry flag means when there is a carry from bit D7, then the carry bit will be set here. Then parity, if the number of 1 are even, then the parity will be set, and if it is 0, then here the parity will be, here this will be 0. It will be 1 for the even parity. Then auxiliary carry will be set when there is a carry from D3, like from, we can say from lower nibble to the higher nibble. 0, if all the bits are 0, then this will be set. Sign flag, if it is a positive, if it is negative, it will be set. Then we have an overflow flag. So overflow flag, this flag is set if an overflow occurs, that is if the result of a signed operation is large enough to accommodate in a destination register, then it will be set. The result is of more than 7 bits in size in case of 8 bit signed operation, and more than 15 bits in case of 16 bit signed operation, and then the overflow will be set in that particular case. Now coming to the trap flag, so used for single stepping. It if set, a trap is executed after execution of each instruction, which displays various registers and memory location content. So if the trap is set, it means after every execution you can check your result. Then interrupt flag, if it is set, then only the interrupts will be recognized. So if we want our interrupts to be recognized, then this interrupt flag should be equal to 1. Then we have a direction flag. So direction flag, if it is 0, a string will be processed from beginning with the first element having the lowest address, and if it is 1, then a string is processed from the high address to the low address. Now coming to the general purpose registers. So the general purpose registers, first is the accumulator register. Preferred register to use in arithmetic, logic and data transfer instruction, used in multiplication and division operation, and also used in IO operations. Then next we have the BX register, which is a base register. This also serves as an address registers. The next we have the CX, which is a count register. So this is used as a loop counter. So whenever we want a counter, we use this register, and it is used in shift and rotate operation. Then we have DX, which is data register, is used in multiplication and division and also used in IO operations. Now coming to the segment registers. So here the physical address of 8086 internal architecture is of 20 bit, because here we have 20 address line. Why to access? So it can access 1 megabyte memory locations, but however, its register and memory location which contain logical addresses are just 16 bit wide. Actually, here we have a 20 bits of physical address, but we can't store this 20 bit in a register because registers are of 16 bit wide. So here what we have done, we have segmented our memory. It treats the 1 megabyte of memory as divided into segments with a maximum size of segment of 64 KB. So we have divided our memory, and each memory segment is of 64 kilobyte. Thus, any location within the segment can be accessed using 16 bits. So why we have segmented our memory? The idea is so that we can create an address of 16 bit. So the 8086 internal architecture, it allows only 4 active segments at a time, and for selection of 4 active segments, the 16 bit segment registers are provided within the bus interface unit of 8086. So for these segments, we require the segment register to store the address of these segment registers. So here we can see we have 4 segment register: the code segment register, data segment register, extra segment register, and stack segment register. So what are the function of these segment register? The code segment register holds the upper 16 bit of the starting address of the segment from which the bus interface unit is currently fetching the instruction code byte. So here we can see the this is our memory, which is divided into different section. So this is a code segment, this is a data segment, this is a stack segment, and this is a extra segment. So the starting address of this segment is stored in these segment registers here. So this is total of 1 megabyte physical memory, and we have divided this memory, and this code segment, all these memories are of 64 kilobyte. So the address of 16 bit can be generated here. Then the stack segment register is used for the upper 16 bits of the starting address of the program stack. Then we have extra segment and data segment register. They are used to hold the upper 16 bits of the starting address of the 2 memory segment which are used for the data. So all these segment register, basically they are holding the starting address of these segments which we have created in our memory. So the 4 segment can overlap for a small program. It facilitates the use of separate memory areas for program, data, and stack. It allows instruction code, data, stack, and portion of program to be more than 64 kilobyte long. Now coming to the instruction pointer. So instruction pointer, the code segment register store the upper 16 bit of starting address of the segment from which the BIU is fetching the current code, and the instruction pointer register hold the 16 bit address, or we can say this is the offset address of the next code byte within the code segment, right? So the instruction pointer, it holds the offset address. So the code segment register, it points to base or start address of the current code, and IP refer to the distance from the base address to the next instruction byte to be fetched. So here we can see the first code byte address, it is stored with the code segment. This is the starting address. Then the second code byte address, this will be stored in the instruction pointer. So this is called the offset address. So the distance from the starting address, or we can say the offset, it will be stored by the instruction pointer. So if again the next, if the third code byte address is 4216, so it will be stored in the IP. So now this is the distance from the starting address. Now coming to the stack pointer. So stack is a section of memory set aside to store address and data while a subprogram is executing. The stack segment is used to store upper 16-bit of the starting address of the program stack. The stack pointer register in execution unit holds the 16-bit offset from the start of the segment to the memory location where the word was recently stored on the stack. So again, the stack pointer register, it holds the offset address. The memory location where the word was recently stored is called the top of the stack. Now the stack segment and the stack pointer. So now consider most recent entry is at FFE0H. So this becomes top of the stack segment, which is pointed by stack pointer. So this will be pointed by stack pointer. So the stack segment, it is containing 500H, which is the starting address, and this is the recent location where the data has been added. So this will be stored in stack pointer. So this is the distance from it. So we can say this is the offset address. Now coming to the base pointer, source index and destination index. So these three 16-bit registers can be used as general purpose register. However, their main use is to hold the 16-bit offset of the data word in one of the segments. So now coming to the base pointer, we can use the base pointer register instead of stack pointer for accessing the stack using the based address mode. In this case, the 20-bit physical stack address is calculated from base pointer and stack segment. So actually the physical address is calculated by the bus interface unit. We actually give the segment address and we give the offset address. So we can calculate the physical address. If we multiply the segment address, the formula is segment address into 10H plus offset address. So this will equal to physical address. This is equal to physical address, right? So segment address into 10 plus offset address, this is equal to the physical address. So this is how the physical address is calculated. So the segment address is also of 16-bit and the offset address is also of 16-bit. So by using 16-bit address and storing 16-bit address, we can actually create a 20-bit address, right? Because here we have a 20-bit address line. So 20 addresses line. So here we can calculate the 20-bit address. Now coming to the source index. Source index can be used to hold the offset of the data word in the data segment. So in this case, the 20-bit physical data address is calculated from SI and DS. Then we have a destination index. The extra segment register points to the extra segment in which the data is stored. String instructions always uses extra segment and destination index to determine the 20-bit physical address of the destination. So these are the index registers, right? So if we before I am concluding, I am coming back to the architecture. I will summarize the architecture once again. So yes, this is the architecture. So here now we will summarize this architecture. Here we can see that this is a bus interface unit and this is a execution unit, and bus interface units contains all the segment registers, right? All the segment registers is here. So we give the segment addresses are stored in these registers. This will be given here, and we will also provide the offset address, and then the physical address is calculated at this particular location, right? So here the address will be calculated, then that address will go through the buses, address buses, then the instruction, all the instruction will be fetched and they will be stored in this registers, and when the instructions they get stored in this queue, they will come to the execution unit. It will get decode, the execution unit will decode it and execute it. It will decode it and execute it through its arithmetical logical unit, and all using all these registers, the execution unit will decode and execute it. It has also a control circuits. So when these two location will get empty, then again the bus interface unit will fetch the next instruction. So the question means it has all these 6 locations are full, then the execution unit is fetching the instruction from this queue. Then when this bus interface unit will fetch the next instruction, so the bus interface unit will fetch the next instruction when these 2 locations are empty, because this location is of 8 bit and this location is also of 8 bit. So when these 2 locations are empty and we have 16 data lines, so in one cycle only we can fill this 2 locations. So when these 2 locations will be empty, then only the bus interface unit will fetch the instructions. So that's all in the in this lecture. So I have, as a reference, I have used the book for 8086, which is Advanced Microprocessor and Peripheral by AKGEC and KM Bhuchandi. This is a very good book for 8086 microprocessor. Thank you. That's all.